Let's learn, try to get through as much as we can.
So like spread out.
We did example 7, am I right?
Yeah.
Okay, so now we just gotta do 2 more and then we're done with unit 9. I might give you, I gotta remember to do this, but I'll print out the unit 9 test that we used to give BC students when that was like class. So that you can check how you like would do on that test. But remind me, of course, I won't grade it for a grade, but you could take it and check. I might make you guys grade it yourselves, but that way you get an idea of how well you understood this stuff. Oh, also the quiz on the very back of your homework. That's the answer key to that is not on Schoology yet, but I'll put it up there as soon as I remember. I may need some reminders because I'm juggling a bunch of stuff. But yeah, I'll put it up there. It's done. You can check it if you want.
Is that
The paper copy I have. Okay, now quick reminder, the last thing we did was integrals of polar functions. And remember the way to get areas in polar functions is not just straight up the integral of the function itself, but it has to be this formula because they come from areas of sectors, which are 1/2 integral of r squared times d theta. And so we did, I think, this example and another example. Oh no, I guess we just did this one. Okay. Well, the last 2 are getting the area between 2 polar curves. So this green area, and even without me teaching you, I think you guys could figure out that would be, well, you can probably see it right here, but yeah, the idea is to get the area within 1 minus the area within the inner function. And that will give you the area between 2 functions. So 1/2 times big radius squared minus little radius squared, which is like top minus bottom, that same idea. Okay, so this one says determine the area that lies inside this and outside of that. And this one's nice because not only did it give you the graphs, but it also labeled them for you, which sometimes they don't do, which is another reason why it's good to know how polar graphs work. But in this case, the blue one in my screen is the 3 + 2 sign, and r = 2 is the red graph. Okay, so to get the area between, I just have to do the integral. Well, 1/2 times the integral of big, like outer radius, outer function, minus inner function squared. Except for 2 things. First, we got to identify what the outer function is and the inner function. And then second, we have to figure out from where to where I'm integrating. So I guess I'd want to go from, remember polar coordinates work like you're rotating like this. So here's the start and here's the end. Except how do I find what like values those are? Do you know?
So they're equal to each other.
Yeah, exactly. That's where the 2 intersect. So here's us doing that off to the side. 3 + 2 sine of theta equals 2. Okay. And then if I start solving this, if I subtract 3, I get 2 times sine of theta equals -1. And then divide by 2, and I get that sine of theta equals -1/2. Okay, and so on the unit circle, we're looking for where the sine of theta is -1/2. Is remember where that happens?
7 power 6 and 1 power 6.
Yeah, this dude right here and this dude right here. So 1, 2, 3, 4, 5, 6, 7 pi/6, and then 11 pi/6, like right before 12 pi/6. 7 pi/6, 11 pi/6. And so like any rotation afterwards. All right, very cool. But if you're working ahead and you said 7 pi/6 to 11 pi/6, then you'd be wrong, because why, you guys?
Then you're just getting like the bottom.
Good job, yeah. Because if you think of it, the unit circle would be like, this is 7 pi over 6. You start there and end here, then you'd be getting this part of the curves. You see what I'm saying? So can you think of a way to make it go from here to here? Nice.
Like you just add 2 pi to 7 pi over 6. So it's like 11 pi over 6 to whatever the next one is.
Oh, okay.
Like you add 2 pi to 7
No,
pi
I
over
see what you're
6.
saying. I guess that would work. I guess that would work. Let me check if that would work. I'm afraid to, I guess, yeah. I don't see why it wouldn't work. Integral from 11 pi over 6 to
I don't know.
19 pi over 6. Oh wait. 1/2 times 3 plus 2 sine minus 2 squared. B theta is 24 point something. What did I get for my answer? 24 point something. Yeah, okay, that nice. Yeah, that's a good way to do it. Or do you see why I was hesitating? You guys have other ideas? That is not what I expected you to say. What are you gonna say, Bert? That's the first thing I thought of, instead of going from 11 to like do a full rotation around and then to 19 pi over 6. Go from negative pi over 6 to 7 pi over 6. That works too. Nice. Yeah, but either way you do it, you should get the same answer. So here's us setting it up both ways. You choose whichever way you like better. We heard first this idea, 11 pi over 6 to 19 pi over 6 of outer function minus inner function. And you guys just saw me spoil it, but hopefully you understood why the outer, the farther one away from the pole is the blue function, and the closer one to the pole, the origin, is the red function. So blue function minus red function. That's a good setup, and that'll give you the answer that we just got, 24.1870. That's good. Or set it up like Bree said, negative pi over 6 to 7 pi over 6 of the same function. Question.
Did you also just do like from negative 11 or negative 5 or 6 to like 5 or 2 and then get rid of the half?
Oh. That was cool. Yeah, I bet you could. Sam saying, since this is symmetrical, could I just get this much, whoop, and then multiply it by 2 so that there is no 1/2 in front? And yeah, that should work too. Nice, good idea, yeah. In fact, I've seen that on the AP test where they say which one of these gives you the area of whatever, and they use that trick that it's symmetrical and you multiply it by 2 or whatever. Yeah, that you could do that. Nice. All right, last questions. All right, okay. And then the next one is the same thing, luckily, like same graph. But now we do want the bottom half of the circle. So see if you can set up that integral. And then I'll tell you the answer once you do. Could be very similar. Oh. You keep working, but I'm gonna be an efficient teacher and pass out these while you guys work. Some tiny unit.
The formula. Because it's derived from. Because it's not derived, it's just derived from the weird things. It's like derived, like he like explained it, but it just made no sense, and I just remember that like the derivation for this one half. It's probably just easier to memorize than it's like the super complex derivation to like get a one half.
Was memorized it.
1/2 in force. This is what's like.
McClellan shoes. That's what that. I've been wondering about the poster like all year.
Yeah, it's up there.
Like a little bit. Like after we see it.
No.
So chill, we only let her go up.
All right, check that you set it up like this or some equivalent way. But now the red function is farther from the origin than the blue function is, so it's red minus blue for the setup. Then don't forget the 1/2. Don't forget the squareds. But outside of that, oh, and don't forget this time we are going from 7/5/6 to 11/5/6. That is the right way to go from here whoop, to there. And then the answer before this question is 2.1958. If you were interested. Question.
Are we probably only gonna ever get these on like the calc part of the test?
Yeah. Yeah, the only time I've seen them is there. Or if it's, yeah, exactly. Or it's a setup but don't evaluate. Question.
Yeah.
I mean, yeah, they're there for a reason. I would have to think of, like, the only one that I've ever encountered in real life, you're not gonna like, but there was a time when in college I had to like we took this modeling class, like model real life things, and they were talking about a bird who swoops in like this to catch his prey.
What it swoop in?
And like that's the path that he took and stuff like that. And I think that was a polar function. But outside of that, I'd have to look it up to the age. Real life applications of polar functions. But well, yeah, I'd have to look it up before I make something up. Question.
What was James' question? I couldn't quite hear.
You said, are these only mostly gonna be on the calculator portion of the test? And the answer was yeah, probably. Or like I said, they'd be set up but don't evaluate type questions if they're not on the calculator section. Cool question. 1/2 comes from the let me see if we still have our notes from that. We
What?
probably don't.
Just taking.
No, we don't have it.
Like
It's cause when you set up the area of a sector,
it doesn't do anything else.
So just to like saturate your
if you get the area of that slice of
Yes, it is.
pizza,
It's not.
you set it up like a freaking, what's it
Who
called?
said that?
Like a proportion.
Okay.
So it's,
I guess-
so
I
it's
guess.
area of this sector over area of the full thing
Like recently, though.
equals
His wife.
this angle of the sector over the angles of the full thing, so 2 pi around the full circle. And then if you solve this 1 over 2 pi is where the 1 half comes from. That's
Science-based.
all right, y'all. Cool. All right. So, like I said, remind me, I gotta print your Unit 9 tests, and you guys can take that. Or even, oh, what if I just post it on School? Well, I'll print them. I'll print them. And then also, I gotta print your Unit 10 homeworks. But as you know, the packets themselves take so long to print that I like to do it one day the packets, one day the homeworks. So homework's coming up soon. But today we won't get super far. We won't even finish the first section on Unit 10 anyway, so you wouldn't be able to do much homework. But here we go. This is a big day. It's your final unit. And it's all about series, which just means, well, here, join me on the first page because it does a good job of explaining what series are. Okay. So series, just so you get an idea of what we'll be looking at, series just means like a sum of like, well, it's helpful to talk about sequences first. So a sequence is just a list of numbers in order. Like the first number is like a sequence, like I said, is just an ordered list of numbers. First number is this, second number is this, third number is this. It's like what you would have called a pattern in second grade or fourth grade or whatever. So like a sequence would be like 1, then 3, then 5, then 7, etc. Whereas a series is the sum of those. 1 plus 3 plus 5 plus 7 plus blah, 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 blah. And it could be finite, like they could be a 4 element list, or it could be infinite. But yeah, a sequence is just the list. A series is the sum of that list. The notation usually they call these like a sub whatever for sequences. So like a sub 1 would be the first number there. Or a lot of times, just for convenience of writing formulas for them, a lot of times they'll call this a sub 0, then this a sub 1, then this a sub 2. Like that's just the way they name them. And then that way it tells you for the sequence A, this is the 0th term. For the sequence A, this is the first term, second term, etc. So you will get used to seeing this notation a lot. At the very least, you'll see what I'm circling right now, that notation. This one is pretty fancy, and you might see it in college, but not so much in our class. Do I want to say anything else? That if, okay, broken down in simple terms, this part about the limit just means that if this pattern has, like if you can see that it's headed towards 0, like let's say we started at 1, then 1/2, then 1/4, then 1/8, then 1/16, etc. You could see that that's trending down towards 0, and that's what we'd call the limit of a sequence. Is like where's that pattern headed to? That's what this is talking about. And they say that if it has a limit, then the sequence converges. Otherwise, it diverges. More on that to come later, but you've heard those words before in improper integrals, unit 6. Okay. All right, that's all about sequences. Then series, like I said, it's good to know about sequences because series are just a sum of sequences. So the sum of all terms is called in a sequence is called a series. An infinite series has the following notation with the sigma. You guys remember hopefully that just means add up all the terms that look like, well, people on the video can't see, but the sigma means add up all the terms that look like that from, in this case, the first term to the infinite term, like for infinite, from the first term to infinite. A partial sum is the sum of only part of the infinite series. And you'll get a better intuition for these as we go along. But basically, the way to take an infinite series is, since you can't be sitting there adding things forever or working with an infinite number of numbers, what you do is you take like a partial sum and see what the limit of that sum is. More on that later, but that's how you deal with infinite sums. And then last thing you gotta know is, again, we say that an infinite series converges if the sequence of partial sum converges to some number s, as in if this adds up to some finite number. Let me say finite result. Then it converges. And if it does not, like if the sum does not exist, like you'll see later, or if it goes to infinity. Then we say it diverges. So most of the time things will diverge because they add up too big and the sum goes off to infinity. Like if you add 1 + 2 + 3 + 4, that's just gonna get enormous and that'll go to infinity. So therefore we'd say it diverges. But sometimes, not to tell you too much too far in advance, but sometimes, like for example, if I add 1 - 1 + 1 - 1 - 1 + 1 - 1 + 1, etc., like this forever, then the partial sums won't ever converge. Because if you take, for example, if you take just the first three, then you'll see 1 - 1 + 1 is 1. But then you take the fourth one and you go to 0, and then you take the fifth one and it goes to 1, and then you take the sixth one and it goes to 0, etc. Because all the ones and minus ones alternate. And so therefore, if I ask you, okay, what's this pattern headed towards, you wouldn't be able to say. Like sometimes it's 1, sometimes it's 0. It's not headed to one particular number. So therefore, we'd say it diverges. Okay, that was a lot of math all at once. If I was a student and I wanted a summary, I would just want to know, like, what do I take away from this? Take away the fact that we're about to be adding an infinite number of numbers and seeing, does that ever get small enough to like add up to a finite number? And take away the fact that if it does add up to a finite number, we say it converges. Otherwise, it diverges. That's the summary. Questions so far? Okay, of course, like I'm sure everybody's still generally confused, but we haven't even done one example yet. So once we do a few, you'll start to build an intuition. So watch this. It says, given the series written right there, find the first 5 terms of the sequence of partial sums. As in, find the sum. Find the first partial sum, the second partial sum, the third, etc., all the way up to the 5th one. So take the first term, that's the first partial sum. So people usually call that sum of 1 is equal to. If I just take the first term in this series, then I just get 3. Okay, that's the first partial sum. The second partial sum means take 2 terms and add them together, which would be 3 + 5. So let me circle the final answer so that we can see if these are headed anywhere. Third partial sum would be 3 + 5 + 7. Take 3 terms and add them together. And that would be 15. Then the fourth partial sum would be 3 + 5 + 7. Plus, you tell me what the fourth term would be just to make sure. Okay, yeah. These are just the odd numbers, but if you didn't know, you could just plug in 1 into this. 2 × 1 + 1 is 3. Then plug in 2 into this. 2 × 2 + 1 is 5. Then 3, then 4, and that's how you get all the terms. In case you forgot how sigma notation. All right, and that would give me 24, right?
Yeah.
And then sum of 5. The 5th partial sum would be the 5 terms, first 5 terms added together. 11, which would give me 35. And there, I've answered the question. Find the first 5 terms of the sequence of partial sums. Okay, it'd be 3, 8, 15, 24, and 35. Those are the first 5 terms in the sequence of partial sums.
Fibonacci sequence.
Okay,
Yeah.
Then it says, does the sequence of partial sums converge or diverge? As in these numbers that I've circled, where are they headed?
Up and up and up.
Yeah. By more and more and more and more and more. So yeah, these are never gonna end up tailing off to a certain finite number. These are just gonna get bigger and bigger and bigger and huger and by more and more each time. So, well, let me ask you, does it converge or diverge then? Converge. Boom. Cool. Okay, then part C, you're gonna say, oh, there's a typo here. You asked the same thing twice. And I kind of did, but not really. It's a little subtle difference between part B and part C. Part B says, does the sequence of partial sums converge or diverge? It diverges. And so therefore now, because this diverges, you can answer whether the whole sum as a whole, the one that goes from 0 to infinity, whether that converges or diverges. It's a little bit of a subtle difference in question, but they're gonna have the same answer both times, because if whatever happens to this determines what happens to part C. So for part C, does this whole series, the original series, converge or diverge? Well, since the part B diverged, then of course this diverges. Yeah, if you're confused about that, you'll get more of an intuition. I would just hesitated because I was like, should I explain more into this? But I think it's better to just not and just let you build intuition as we build more examples. But yeah, question.
Would there be other ways to find out if the series is divergent? Because with the series, you can look at it and see the function will never like slow down.
Yeah, that's what this whole packet is about, is like different methods of seeing just by looking at it or doing some math on a series, if it'll converge or diverge. So yeah, good, like foresight or whatever. That's what's coming up. All right, the series in this example is called an arithmetic series, which is the terms of which are determined by adding the same constant amount to the term before it. So do you think there are any convergent arithmetic series? So what this is saying is like basically that we got the first term was 3, then the next term was 5, then the next term was 7. So it's arithmetic because they keep increasing by the same amount. It's like a distance of 2 between each one. Okay. So basically, if the formula for them looks like a linear function, that's going to be arithmetic. So can you think of a way to make that converge, or do you think that they will never converge?
Wait, it's also split.
Okay.
Can't wait, like, can't it, in your arithmetic?
Subtraction in what way? Like 5, then 3, then 2.
Like, I did.
Yeah, I think that counts as arithmetic.
That's what I thought, so you just said add.
Oh, got you. No, yeah, but subtraction works. But did you think of a way to make it converge?
I think,
How?
is it, maybe I don't know, that's,
What did you say?
I said like 2n plus 1 minus 2n,
Oh,
but that's what I was asking.
that's actually
Oh, wait, then wouldn't it?
a technicality, yeah. Okay, well. So you're saying, if we use this sum, 2n plus 1, the same one we started with, but minus 2n, then technically, I guess that's arithmetic. But then you get the sum, like that's the same as the sum, like if you simplify this and this. Then you just get the sum of ones, which actually still does not converge because then you're adding 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. So still it doesn't converge, but maybe if you just like subtract this, if you just count this as an arithmetic sum, okay, then of course 0 plus 0 plus 0 plus 0 plus 0 is going to converge. But anything else is just not any other arithmetic series, no matter if you're going like, if you're starting at 0 and then you add 0.00000001 and then add 0.00000002 and then et cetera, et cetera, et cetera, et cetera. Even that is just not like getting small enough to converge. Otherwise, let me say that. So again, even if you count like the sum from 1 to infinity of like 0.000001 times n. Like however many zeros this is, 1, 2, 3, 4, 5, 6. Okay, perfect. If once you get to a million terms, that every time you get to a million terms, you're adding a whole number. And so every million terms, you're adding 1 plus 1 plus 1 plus 1 plus 1 plus 1. And so it's just going to grow forever. And no matter how small you make the difference, arithmetic sequences won't converge.
Are there
Question.
times where like the sequence will converge, but then the series diverges, or like vice versa?
Yeah. Wow. What a great question. Oh my gosh. Great thinking. And that's coming up in a second. Yeah, but Sam said, will ever the terms go towards one specific number, the terms of the sum, but when you add them all together, they don't converge? And the answer is yeah. Like, so the terms of, like, for example, if you want a quick preview. This dude right here has a special name because the terms of that are 1, then 1/2, then 1/3, then 1/4, etc. So these are all going to where? You tell me.
0.
Yeah, of course.
It actually equals 2.
But wow, yeah. If you add these all together, then it actually diverges. The thing that equals 2 is different.
Oh, that's a different one.
That'd be this one, I think. That one equals 2. Well, yeah. All of this you'll know in a few days. Nice, you guys. Well, I guess that's as far as we got, but I'm glad, like, these are really good questions and good. Shows good thinking. All right, yeah, let's stop there. We'll pick up on Monday.
That's how.
And I'll get you your homework by Monday as well.
See, Sam,
What?
the towel looks like a dog.
Wait, are we not coming in tomorrow?